So we're going to loop back to the results of the Maxwell equations one more time and recall that light is a wave. And just like in mechanics, where we've seen that mechanical waves could exhibit diffraction, the same is true for electromagnetic waves. So it's probably worthwhile spending a moment reminding you of how Huygens Principle works. So Huygens Principle says that each point on a wavefront is a source for spherical wavelets. These wavelets will interfere to make the next wavefront. Now, for two particular arrangements of wavefronts, this will work out to make wavefronts that look like themselves again. So we can look at plane waves. So here the wavefront is, quite literally a plane. And so what Huygens Principle is saying is every single point on here can be viewed as a point where we propagate what we call wavelets. Just basically, we think of it as a source of waves. Now these wavelets will propagate both forward and backward, and they will be spherical. But we'll only really concern ourselves with the wavelets that are with the part of the wavelets are propagating forward. This is because you can show, but it's beyond the scope of this treatment, that the bits of wavelet that are propagating backward will always destructively interfere out. But going forward, that isn't the case. So these wavelets will propagate out like so. There we go. And a little further along, they'd start looking like this, maybe. Sorry, I know my art isn't the best. All right, but anyway, these will all, right here, you see will constructively interfere. If my art were good enough to show it, we constructively interfere to make the next wavefront, like so. And then exactly the same thing happens. Every point on this wavefront will act as a source of wavelets, and they propagate forward and make the next wavefront, and so forth. So this is a very good model for thinking about how wavefronts will propagate forward. The other kind of wave that will end up looking like itself, or at least to within a size issue, are spherical wavefronts. So again here, just like here, I was drawing in cross-section, but you should think of this as a plane going in and out of the screen. Here I will be drawing in cross-section, but you should be thinking of it as a sphere in 3 dimensions. And again, it's the exact same game plan. Every point on here is going to be a source of wavelets that will propagate forward. Just trying to make it look, oh, there we go, something like that. And so it's going to be the same process that these wavelets will just propagate forward. They're spherical. Again, beyond the scope of this treatment, you can show that the wavelets heading backward will interfere themselves out, and you'll just be left with what's going forward. So you end up with something, say, looking like that. And we see that our spherical wavefront is propagating out uniformly in all directions. So in the early days of the development of the theory of light, there was a big argument about whether light had a wave or a particle nature. Now it turns out, spoiler alert, that the modern view is to say that light has both a wave and a particle nature. And in fact, literally, so does everything else. All matter, etc., have both wave and particle natures. And the modern interpretation is that the wave nature of the light dictates the probability of where we would detect the light particles, which we call photons. So where the amplitude is greater, either up or down, because it turns out to be the square that matters. Where the amplitude is greater in absolute value, you'd be more likely to detect a photon in that position. That's the modern interpretation. But it wasn't until the 20th century that people realized that the wave or particle thing was a false dichotomy. So in the debate on this, Newton was probably the most famous person to hold that light had a particle nature. His argument for this was that if you look at your shadow, you should see a diffraction pattern off the side of the shadow. Just like when you're doing diffraction for water waves, it would be no different. So he posited that since you didn't see that diffraction pattern, that excluded the possibility of it being a wave. Other people, like Huygens and others, argued, though, that many of the things that you see light do would be better explained with waves, and it's more torturous to explain them with particles. And so the big test came out, this thing called Huygens experiment. And this is actually something you can do at home if you've got a piece of aluminum foil and an X-Acto knife. What you do with your aluminum foil. So say this is your piece of foil here. I mean, Young did this much fancier, but this is the idea. So say if you take like your foil sheet or something like that, you make 2 slits with your X-Acto knife as close as you possibly can to the foil. And then you can look through the slits at a light source. And don't look at the sun through this. Believe it or not, even though this blocks out most of the sunlight, what would get through would still be enough to fry your retina. But say looking at a street light or a house light, something like that, that'd be totally fine. And if you do, you should see, some spectral patterns coming out. You should see some of the colors of the rainbow happening. We'll get into how that works in a bit. So what's going on here? Pardon me here. So this photo here, actually let's not do it there. So what's going on here? How are you seeing that effect? Well, if we draw this from the side, if you're using like a street light or something like that where you're reasonably far away, the light that will be coming into your pair of slits, so these two gaps here are your slits, will be well approximated as a plane wave. Like so. Distance between successive crests will be the wavelength. Now, what's happening is when you go through the slits, the light gets blocked everywhere except where there's a slit. And so by Huygens Principle, the only place where we can be emitting wavelets from are going to be from the slits. Now, the way this is going to interfere out is they're going to look cylindrical-ish with a little bit of curvature at the top and bottom, so maybe like a multivitamin capsule or something like that. But we can just focus on the mostly cylindrical part of it because usually we make the slits rather long compared to their separation. So the idea is, in here, let me draw the wavelets in different colors just so we can kind of tell them apart. So these will be the wavelets coming from the upper slit, and then these will be the wavelets coming from the lower slit, like so. Now, you'll have constructive interference anywhere where you say have crest meeting crest or trough meeting trough. So something like that. We should have had more in the way of crest, crest, cross. You know, there's a trough, trough there. But again, that's sorry about my art. And then if you go and say put this on a screen, or actually don't even need to, you can just look through the slits and use the retina of your eye as itself as the screen. What you'll see is something that looks like this. Now here I shined red light through a pair of closely spaced together slits, and the camera is actually just looking right through the slits, so the interference pattern is being made on the CCD array. Now you'll notice that there is a bright central maximum, and as you go away from the central maximum, it falls off. You'll also notice that you'll get to a spot where it gets dimmer and then it starts to get a little brighter again. Hold that thought for a future video. We'll loop back to that. So what do you think would happen if I changed the color of the light from red to blue? Blue light has a shorter wavelength than red. So go ahead, pause the video, make your prediction, and we'll see what you get here. All right, so this is what happens when you use blue light. And here you can definitely see that the pattern gets dimmer as you get off to the edges and it starts to get a little brighter again. Like I said, I'll explain what's going on with that in a future video. But you should notice right now that the spacing of the bright fringes is closer together when it's red, when it's blue, than here when it's red. Red, it's farther apart. Blue, it's closer together. All right, so what's going on with that? Well, so first off, just for some notation, let me just kind of note the intensity of the light that we see. I'm just going to make a graph like this, and wherever you see a peak, is where we saw a bright spot in the photograph. So this will get called the central maximum. And we will assign it a number. The name of the number is M, and we'll say it's 0. So this isn't a mass, it's just, we're just using it as a way to hold an integer. And then here on either side, this would be m equals 1, and this is also m equals 1. Here, this is m equals 2. That's also m equals 2. This gets called the first maximum, the second maximum, and so forth. All right, so can we figure out where to locate these? Yeah, absolutely. If we really zoom in on this, the deal here is that if we're going to have constructive interference, again, this is just like, say, when we were doing sound waves in mechanics. The idea with having constructive interference is that the difference in path length, say from here to here and here to here, has to be an integer number of wavelengths. Now here, the difference, if we call this one L1 and this one L2, L2 minus L1 is just plain 0. Well, that's certainly an integer number. And then say if we look at it over, I don't know, here, let's say, again, this is L1, that's L2. So here, let's actually just think about this in absolute value because that's all we really need. Oops, there we go. Absolute value of L2 minus L1 here would just be a wavelength. Then over here, if I were to draw it out, the difference in path lengths from the two sources would be 2 wavelengths and so forth. And the idea is that, say, if the extra distance from here to here versus here to here is 1 wavelength, then if I emit a crest here, I am also emitting a crest here, just not immediately. It's just a crest that came 1 period later. But they will both meet up and constructively interfere over here. All right. So now in practice, this separation here, which we will call D, in practice, this separation D is really small compared to the distance to whatever screen or viewing device you're using. So typically, D is much less than L. And this will let us cheat a little bit here. So if D is much less than L, then what it means is that when I'm looking at a pair of rays coming out, these rays are very nearly parallel. Or, sorry, the path lengths from the one slit to the other. These are eventually going to meet to constructively interfere, but these are almost parallel. This means that the extra distance traveled is what you get if you drop almost a perpendicular. So we're just going to make it a perpendicular. And then say this extra bit right here is the excess distance traveled. That's our L2 minus L1. Now, D here is the distance between the slits. So if this angle here down, from between the two slits out to wherever the peak is theta, this would be D sine theta. Now, this is also going to be equal to an integer number of wavelengths. It's going to be 0 if it's the central max, 1 if it's the first max, 2 if it's the second max, and so forth. So this is going to be equal to m times lambda, where m can run from 0, 1, 2, 3, etc. So now the trick here is that since the D is so much less than L here, it turns out that any angle you're going to measure is going to be very small, typically no more than a degree or 2. So we can say typically theta is small, which means in radians, and you do have to work in radians if you use this approximation, the sine of theta is approximately theta itself. So we can say, all right, then the sine of my angle was m lambda over d. And then usually what we do is we say, oh, but typically the angle for my mth constructive maximum is approximately m lambda over d, and that's in radians. By the same token, if we go back here and say that the distance from the central max to whatever max we're interested in, so this would be y, and this would be y2, for instance, we can locate those by saying, oh, that's going to be a tangent there. We can say that ym would be equal to L tangent theta. But again, in radians, tangent theta is also approximately theta itself as long as the angles are really small. So we can go ahead and say that ym is approximately L theta m, which would be equal to m lambda over d times L. And again, which would be equal to m lambda over d times L. And again, m would be equal to 0, 1, 2, 3, whatever. So if you want to know where the dark fringes are, they are exactly in between. Alrighty, so let me bring back this picture here. And so I'm going to ask you, what do you think will happen if the if I make the slit spacing closer together? Yeah, the interference pattern actually gets more spread apart, which makes sense because D is getting smaller and it's in the denominator. Alrighty, so in the next video we'll go ahead and take a look at Young's experiments, bigger sibling, the diffraction grating, and see how we can use that to identify unknown chemical elements. Catch you over there.